How does the X-ray photon beam look like? How do you imagine an X-ray photon beam? I know it is invisible, but if it was visible, how would you describe its appearance? Have you ever thought about it? When you sit at the console of your linear accelerator machine and press the beam on button, what do you imagine? Many of you might imagine an X-ray photon beam to be like a steady, continuous wave of light, like this. Or many of you might imagine it to be a solid, unbroken laser beam, like this. But as radiation oncologists, we must understand the physics reality. The clinical megavoltage X-ray beam is not a continuous ray of light. It is not even like a laser. We must completely stop visualizing it that way. Instead, you should picture the beam as a huge collection of individual discrete packets of energy. Once again, a huge collection of individual discrete packets of energy. We call these tiny packets photons. Photons. Think of the beam as a heavy shower of billions of small raindrops. They are traveling independently through space. These photons have three key properties you must remember. First, they have zero physical mass. Second, they have zero electrical charge. Third, they travel extremely fast, exactly at the speed of light. To properly understand and measure this beam for treatment, we must do three specific things. We must capture, count, and weigh these X-ray photons. This is exactly how we define the beam in medical physics. We just saw that the photon beam is a massive shower of individual X-ray photons. Next immediate question which arises is how to measure the strength or amount of radiation of this X-ray photon beam. We must measure this beam properly to treat our cancer patient. I mentioned three simple terminologies to define an X-ray photon beam. These are how to capture X-ray photon beam, how to count X-ray photon, and how to weigh these photons. But what exactly do these words mean in our daily clinical physics? First, we must count them. What does it mean to count the X-ray photons? When we say count, we are talking about measuring the fluence of X-ray photon beam. Fluence is a very important concept. It is simply a strict count. We count how many individual photons pass through a specific area. Imagine a 1 centimeter by 1 centimeter square in the air. The fluence is the total number of photons passing through that square. Second, we have capture. When we say capture, we are talking about radiation detection. Radiation detection is how we know the beam is actually there. To do this, we place a special radiation detector far away from the machine. Then we place a block of tissue between the source and the detector. A photon might travel straight through the tissue without interacting with any atoms. If it does, our detector captures and counts it. But the photon might also interact with the tissue. It can be completely absorbed or it can be scattered off the side. If it scatters away, it completely misses the detector. This simple setup is exactly how we measure the attenuation of our clinical beam. Third, and very importantly, we must weigh these photons. What does it mean to weigh them? We are talking about measuring the energy fluence and the intensity. Our clinical linear accelerators produce a polyenergetic beam. This means the photons do not all have the same energy. Some might have 1 MeV, others might have 6 MeV. Because they are not equal, just counting them is not enough. A simple count does not tell us the true biological dose. We must calculate the total sum of their energies. We add up the energy carried by all those individual photons having different energies. Imagine this total energy passing through our 1 centimeter square every second. That measurement gives us the true intensity of the beam. This is also called as energy fluence rate. Let us use a simple clinical analogy. This will make it very easy to understand these three words with regard to X-ray photon beam. Think of radiation beam as a line of cars on a highway. Cars on highway. Counting the photons is like standing at a toll booth and just counting how many cars crosses toll booth. Weighing the photons is different. It is like counting the total number of passengers in those cars. This is our first important metric. It is called particle fluence. What does this term actually mean? Imagine drawing a tiny invisible square in the air. Let us say this square is exactly 1 centimeter by 1 centimeter. This one. We want to know how many X-ray photons pass through this specific window. Particle fluence is strictly defined as the total number of photons crossing this given area. In your physics textbooks, you will see the mathematical formula. The formula states that fluence equals n divided by a. Here, n stands for the total number of photons and a stands for the cross-sectional area. You must remember one very important point here. This measurement is strictly a simple head count. We absolutely do not care about how much energy these photons are carrying. We also do not care how long it took for them to cross our window. In our daily practice, time is a very important factor. We need to know exactly how fast these photons are arriving at the tumor. This brings us to our next important metric. It is called the fluence rate. You will also see it written as flux in many of your physics textbooks. What does fluence rate mean? Imagine we take that exact same 1 by 1 centimeter square in the air, this one, but this time we add a stopwatch to count. Fluence rate is strictly defined as the number of photons passing through this given area per unit of time. Per unit of time. In most clinical calculations, we measure this this in photons per second. Please remember, we still do not care how much energy these individual X-ray photons are carrying. To make it easy to remember, let us use a simple analogy. Think of the X-ray photon as cars driving on a highway. Measuring fluence is exactly like standing at a highway toll booth. You are just counting the total number of cars that cross this toll booth all day. You do not check how fast they are driving. You also do not check the number of passengers each car is carrying. If exactly 100 cars cross this toll booth, your particle fluence is exactly 100. For basic fluence, you are just counting the total number of cars crossing the toll booth all day. For fluence rate, you are still standing at that exact same toll booth, but now you are holding a stopwatch in your hand. You are counting exactly how many cars cross the toll booth every single minute. It is the exact same head count, just measured against a strict time limit. During this step, we still do not care about the number of passengers inside those cars. We are strictly measuring the rapid rate of their crossing this toll booth. We have learned how to simply count the photons. But this simple counting has a major clinical problem. Our clinical linear accelerators produce a polyenergetic beam. This means all the X-ray photons are not created equally. If you look at the diagram, some photons carry high energy like 6 MeV. Other photons carry low energy like 1 MeV. If we truly want to find out the energy a particular X-ray photon beam is carrying, just counting the total number of photons is not enough. A simple count will never tell us the true biological dose delivered to the tumor. This brings us to our next important metric called energy fluence. Energy fluence. Energy fluence takes the total number of photons passing through our specific cross-sectional area. But instead of just counting them, it adds up the total sum of all their individual energies. This is the step we previously called weighing the beam. Let us go back to our car analogy to make this very simple. In a polyenergetic beam, some cars are small, some are very large. Counting the cars at the toll booth does not tell you how many people are actually arriving. To know the real impact, you must count the total number of passengers sitting inside all those cars combined. In our physics reality, these passengers represent the actual energy. Energy fluence looks at the actual payload being delivered, not just the vehicles. It measures the true amount of energy passing through this window. We have just learned how to calculate the total energy passing through that 1 by 1 centimeter square window. We called this energy fluence. But we must remember that treating a patient is a dynamic process. Time is always a critical factor in the clinic. This brings us to the ultimate metric of the beam. It is called intensity. Intensity. Some people call it energy fluence rate. This single word represents the true practical strength of your treatment beam. What does it actually combine? It combines absolutely everything we have discussed so far. We take the total sum of energy carried by all the X-ray photons. We measure this total energy passing through our 1 centimeter by 1 centimeter square. But now we add the stopwatch to measure it per unit of time. Look at the master equation at the bottom of the slide. Intensity equals total energy divided by area divided by time. Let us return to our simple car analogy. You are not just standing at the toll booth counting the total number of passengers arriving all day. You are calculating exactly how many passengers cross that toll booth every single minute. This gives you the true powerful delivery rate of the beam. Why is this specific word so important for you to remember? When you are in the clinic discussing a patient plan, you will often use the word attenuation. You might say the beam is attenuated as it travels deep into the tissue. When we say the beam is attenuated or weakened, we are specifically talking about the reduction of this intensity. We are measuring how much total energy is lost from our window every second. This is the core concept of beam attenuation that we will carry forward. Let us summarize all that we have studied. We have discussed several important metrics to define the photon beam. Now we will bring everything together in one simple matrix. This summary table will be very helpful for your quick revision. First, we have particle fluence. The core unit here is strictly the number of individual photons. It only looks at the specific spatial area, completely ignoring time. Our clinical analogy is simply counting the total cars crossing a toll booth. Second, we have the fluence rate, which is also called flux. We are still just counting the total photons crossing an area, but now we add the time factor to it, which means we measure against time. Our analogy here is counting exactly how many cars pass every single minute. Third, we move to energy fluence. Here we stop counting the vehicles and look at the total energy sum. We are still looking at our fixed spatial area without a time limit. Our analogy here is counting the total number of passengers sitting inside all those cars crossing the toll booth. Finally, we reach the ultimate metric, which is beam intensity. It measures the total energy sum passing through our fixed area, and it strictly measures this energy delivery per unit of time. The analogy is calculating the total number of passengers crossing that toll booth every single minute. Please take a moment to memorize this simple table. We must ask ourselves a very practical question. Why should a radiation oncology resident deeply care about these physics terms? They are for physicists. Why should a radiation oncology resident understand it? Because to master medical physics, you must first break the clinical illusion. You must stop seeing the treatment beam as a continuous wave of light. You must see the treatment beam as a massive shower of individual X-ray photons. First, we must learn how to count the photons. This simple count is called particle fluence. It is your very first step in understanding true beam physics. Second, we must calculate the true power of the beam. Remember that our clinical linear accelerators produce polyenergetic beams. This means not all photons carry the exact same amount of energy. If you only know the simple count of the photons, you cannot predict the actual energy delivered to the patient. You must understand energy fluence to know the true destructive power of your beam. Third, we use this concept to measure the attenuation. As radiation travels deep into the patient's tissue, it gets naturally absorbed and weakened. When we say beam is attenuated, we are specifically measuring a drop in its intensity. Without understanding this drop in intensity, you cannot predict how tissue density affects your daily treatment plans. Finally, all of these concepts build the absolute foundation of dosimetry. Dosimetry is the accurate measurement of energy deposited inside the patient. By understanding how these metrics work together, you can confidently evaluate the exact biological effect. You will know exactly how the radiation will destroy the tumor while safely sparing the surrounding healthy tissues. This brings us to the end of today's session. Thank you for watching. See you in next video. Signing off, Parveen Ahlawat.